Hi everybody. So here is a little bit of a supplement to the 16.1, 16.2 lecture that you'll need to be able to solve some of the problems we're going to be working on. So the first thing I want to amend to my last lecture is phase changes. So when a substance is going through a phase change, so it's either freezing or melting, vaporizing, those are the flat areas on our phase diagrams. You can't use Q equals MC delta T. So what you need to use is the latent molar heat of melting, or what we call the molar heat of vaporization. And that is a value that you will find on a lovely little table that looks like this, which I happen to be giving you. And that's where you'll find the values. So for any time that something goes through a phase change, so if I have my graph here, and let's say it's water, and if we're going from a freezing, so let's say we have negative 20 degrees is what we're starting at, this first part is going to be 0 degrees Celsius. So this is where melting takes place and also freezing. And then over here we're going to have 100 degrees Celsius, and that's where boiling for water takes place. So that's going to be this part right here. It's going to be vaporizing or condensing. Now, anytime you have a temperature range that goes through one of these phase changes, you have to use this equation right here. So it's going to be the heat, or the heat of vaporization, equals the moles of the substance times the molar heat of the phase change. So this is going to be what you're going to find on the table. So you have to look at a table or look up the value to get that. So in reality, if you have, let's say we'll call this section A, this first flat part B, C, D, and E, we would have 5 problems to solve if we had a question that said we went from negative 20 degrees Celsius to, let's say, 300 degrees Celsius. So we would have 5 separate equations, and then we would sum them all up to get our total. So let's check out a problem. So how much heat is needed to melt 180 grams of sodium? So I have 180 grams, that's what I'm starting with. Now we need moles because our equation is the moles times the molar heat of melting or vaporization. So our sodium has 23 grams in 1 mole, and now we have moles. And that gives us 7.83 moles. Now, we need to look up the melting point. So, I don't know if you can see this, but we have the molar heat of melting, and on this table we have kilocalories per mole and kilojoules per mole. So I'm going to find sodium, and if I come over here, I'm going to use kilojoules. I'm going to use 2.64. So that's going to be times 2.64 kilojoules per mole. And this will give us, if we use our handy dandy calculator, we have 7.83 times our 2.64, and that's going to give us 20.67 kilojoules of heat required. So that's how much is required just to melt sodium. So to melt sodium, that's what we need. Now, because we weren't going from a temperature, see how there's no temperature in this problem? We're just going through this flat part of a phase diagram. So no temperature change when something's melting or freezing or condensing or vaporizing. No temperature change. And that's why there's no temperature change in the problem. That's why there's no temperature change in this equation. So if you just going through melting, freezing, condensing, vaporizing, you're going to use this equation right here. Just moles times the molar heat of either vaporization or melting. So next thing is the combination changes. So I kind of touched on this. And this is when you're going through several phase changes or at least one phase change. So many times problems we have involve temperature and phase change. So we're going to add up all the heat changes for all the steps, and that's the answer to the problem. So once again, if we started with our diagram, if this is solid down here and this is liquid, this would be gas. So if we had a solid at a temperature below its melting point, so this is its melting point, then you'd want to change it into a gas above the boiling point, so somewhere up here. Then we'd have to go through 5 steps to solve it. First, we'd have to have heating the solid to the melting point. So we'd have whatever our final temperature is, so that would be the melting point. In this case, if this was H2O, it would be 0, because 0 is the melting / freezing point. So we would have 0 as the final temperature minus whatever they said it started at, so let's say -20. And that's, we'd be using Q equals MC delta T, because there's a temperature change. All of the sloping sections, we use Q equals MC delta T. So we use that here, and here, and here. And the plateaus, we're going to use our Q equals moles times the molar heat. In this case, you can say vaporization. Alright, so first step is we have to get A. So we're heating the solid to the melting point. If this was water, it would be 0 minus -20 plugged into here. Then B, now we've hit the melting, so we've hit the flat part. So we're going to use the moles, or we're going to get moles, and then look up on our handy dandy chart whatever the delta H of melting is. Next step, we got to heat the liquid to its boiling point. So in this case, if this was water, we'd have a final temperature of 100, because that's where it melts, minus our 0. And then we'd use the specific heat of liquid water. So if you'll notice, liquid water, solid water, and gaseous water all have different specific heats. So you have to use the right one. So here, we're going to have the specific heat for solid, which if we use joules per grams degree Celsius would be 2.03. For here, now that this is getting quite crowded, it's liquid, so we're going to use the liquid water, and that specific heat is 4.184 joules per grams degree Celsius. So once we do our Q equals MC delta T for this one, we're going to have to do the Q equals moles times the delta H of vaporization, which for water, if we look down here, molar heat of vaporization for water is 40.7 kilojoules per mole. So you have to be very cognizant of what the units are, because they switch specific heats in joules generally, or calories, and the molar heat is in kilojoules or kilocalories. So you're going to have to change them so that when you add them up, you're adding all the same thing. And then our last step is to find the heat of vapor to the final desired temperature. So whatever the final temperature is that you're told, minus 100 in this case. And then we're going to plug in our specific heat for gas, water, which is 2.0 joules grams degree Celsius. So here's a combo. I highly, highly, highly recommend, as in you'll have to do it on your test, drawing the phase diagram so you can see what phase changes it's going through. It's going to be really helpful. Alright, so let's take a look at one of these problems. So first I'm going to draw the phase diagram. It wants us to take water from negative 40 degrees Celsius to 300 degrees Celsius. So I'm going to have my multi-step phase diagram. Here is my 0 degrees Celsius for the freezing point of water. This plateau is my boiling point at 100. Now, let's check this out. Wants to go from negative 40 up to 300. So we're going this direction. Now, if it said we were going from 300 degrees Celsius to negative 40 degrees Celsius, we'd be going this direction, and we'd have to switch the signs on our molar heats of vaporization. We'd have to do that because we're not putting in that amount of energy, we're actually releasing that amount of energy. So direction matters, signs matter, and you'll see more as we practice. So I'm going to label these. I'm going to actually use a different color. So we'll have A, this slope's going to be C, and E. So the blue is going to be our Q equals MC delta T equations. And now our purple, so we have our B and our D. This is going to be our Q equals moles times the molar heat of our phase change, so either vaporization or melting. So our problem, we're starting off with 180 grams of water. So we have A, Q equals 180 grams times our specific heat, and since A is our solid section, we're going to look at our handy dandy chart, and our specific heat for solid water is 2.03. I'm going to use the one with joules, so I have 2.03 joules per gram degree Celsius times our change in temperature. So our final temperature for this phase in this section is going to be 0. I'm going to minus my negative 40 because that was my starting temperature. Now when we crank all this out, we get 14,616 joules. So there's step 1. Now let's move on to B. Here we're going to use our purple equation. So we have Q equals moles. So since this is melting, there's no temperature change. We're going to take our 180 grams, and if I divide by the molar mass of water, which is 18, that's going to give me moles, times the molar heat of vaporization, of melting. So I'm going to look for the melting one, since that's what we're doing in this phase. And for water, we have 6.02 kilojoules. So 6.02 kilojoules. And that is going to give me 60,200 joules. So I got 60.2 kilojoules, and then I just multiplied it by 1,000. to get our joules. Now C, once again we do have a temperature change, so we're using Q equals mc delta T, same mass. Now we have the specific heat of liquid water, which is 4.184, and our temperature change, this time our final is going to be 100 degrees and our initial is going to be 0. If we multiply all that out, we get 75,312 joules. Now for D, this is where we're boiling, so we're vaporizing, going to a gas, but there's no temperature change. All the energy is going to breaking those bonds. So we gotta get our moles, so just like before, times our molar heat of this time vaporization, because that's what we're doing, we're vaporizing, and that happens to be 40.7 kilojoules per mole. And with my conversion to joules, I get 407,000 joules. And our last step is going to be heating our steam. So we're using Q equals mc delta T one more time. And the specific heat for steam is 2.0 joules gram degrees Celsius. And our temperature change, our final in this problem, it says we go up to 300 degrees Celsius minus our 100 degrees Celsius, because that's where we ended, and that will give us 72,000 joules. Now, to finish the problem, you have to sum up the energy from all of these. Make sure that you are aware of all sign changes and anything like that. And if you do that, you get 629,128 joules, and I converted that back to kilojoules just because it's a smaller number. So yes, these are lengthy problems, but you definitely want to draw this. I want to see it on your test, and it'll help you out. One last section that we need to look at is the law of conservation of energy. Because it says that energy is always conserved, in a closed system, whatever something loses, the other part has to gain. Therefore, we can say that the heat lost equals the heat gained, and as such, that means that our Q, so our Q from our mc delta T, that we can set those equal to each other, because whatever one part loses, the other gains. So if we substitute what our Q's equals, we have negative, and this is very important, don't forget the negative, the mass of the one that loses the heat times the specific heat of the item that loses the heat times the temperature change gives us the mass of the one that gains times the specific heat of the one that gains times the delta T of the one that gains. And don't forget, delta T equals T final minus T initial, and we can separate that in our equations so that we can solve for either the final or the initial temperature. So here's a sample. It says, suppose a piece of iron with a mass of 21.5 grams at 100 degrees Celsius is put in an insulated container of water. So the mass of the water is 132 grams, and the temperature before adding the iron is 20 degrees Celsius. What's the final temperature of the system? So we're going to use our negative Q equals Q. Essentially, we're doing two mc delta T's set equal to each other. So I have negative. I'm going to start with what loses. So the iron is going to lose the heat. So we have 21.5 grams for the iron. If you look up iron on your handy dandy chart you're going to have, you'll see it's 0.460. That is going to be joules per grams degree Celsius times our temperature change. So we don't know what the final is, so we're going to put X for the final, minus the initial, which was 100 degrees Celsius. So now this side is good. We're going to set that equal to the one that gains this energy, and our mass of the water is 132 grams. Specific heat of liquid water is 4.184. And our temperature change for this, we don't know what our final is, but we know the water started at 20 degrees Celsius. So now what we need to do is we just need to simplify so that we can get X. Because X is going to be the same for both of them because it's going to reach equilibrium. So we only have to solve for X, and then we'll know the final temperature of the whole system. Now, I have faith that you guys can simplify this, and when we simplify it, the answer I believe we get is 21.41 degrees Celsius for the final temperature. So just make sure that you don't lose this negative sign or your answer will come out wrong. So hopefully this helps so that you can make it through the problems, and everything should just be a variation on this. So good luck, and I will talk to you later.